G'day, in this video we're going to do an example where we make use of the second derivative test. The function we're going to use in our example is the function y of x equals x times x minus 2 times x minus 3. And when you draw the graph of y of x equals x times x minus 2 times x minus 3, the first thing you can observe is that it crosses the x-axis 3 times. It crosses the x-axis when x equals 0, or when x equals 2, or when x equals 3, because those are the values of x that you can put into the function and get 0 coming out. So it crosses at x equals 0, when x equals 2, or when x equals 3. And based on the shape of this graph, it's a polynomial to the power of 3, and the coefficient in front of x cubed is 1, so it's positive, which means the graph is going to take this kind of shape. And then it's just going to keep getting bigger and bigger in that direction and smaller in the other direction. So what we can see is that there's kind of two places where the graph is going to have a derivative of 0. Use green. We'll call this point x1. We'll call this point x2. So at the peak of this hill here, and then at the bottom of this valley, we can see the tangent line will be flat. The tangent line will have a slope of 0. So y prime of x1 is going to be equal to y prime of x2, which is going to be equal to 0. So let's go ahead and find out what x1 and x2 are by differentiating y of x and setting it equal to 0. Y of x equals x times x minus 2 times x minus 3. To make it easier to differentiate, let's expand it out first. So this is going to be equal to x, and then we'll expand the pair of brackets. We get x squared minus 5x plus 6. And then, of course, this is equal to, we times each of the terms inside the brackets by x. So that's going to be x cubed minus 5x squared plus 6x. All right, now we're ready to differentiate this thing. Y prime of x, just by the power rule, bring the 3 down, we get 3x squared. Bring the 2 down, multiply by negative 5, we get minus 10x. And then finally, the 6x just becomes 6. So y prime of x is equal to 3x squared minus 10x plus 6. And well, the points we're looking for x1 and x2. Well, for both of these, we have y prime of x1 equals y prime of x2 equals 0. And we can tell from the diagram, because we're going forever in this direction, getting steeper and steeper, and forever in this direction, getting steeper and steeper, we're not going to have any other points where the derivative is equal to 0. So to find x1 and x2, all we need to do is find the values of x for which this derivative is equal to 0. So 3x squared minus 10x plus 6 equals 0. I'm going to use the quadratic formula to solve this. So this is true if and only if, by the quadratic formula, x is equal to negative b, so negative 10, which is 10, plus or minus the square root of b squared, so negative 10 squared, which is negative 10 times negative 10, which is 100. 100 minus 4 times a times c, so 4 times 3 times 6. So 4 times 3 is 12, times 6 is 72. So 100 minus 72. And then this whole thing is divided by 2a, so divided by 2 times 3, which is 6. And so that's equal to 10 plus or minus the square root of 28 divided by 6. Now the square root of 28, because 100 minus 72 is 28, the square root of 28 is approximately 5.3. So we got 10 plus or minus, so this is approximately equal to 10 plus or minus 5.3 divided by 6, which is 15.3 divided by 6, or 4.7 divided by 6. So 15.3 is 10 plus 5.3 divided by 6, and 4.7 divided by 6 is 10 minus 5.3 divided by 6. And so that is approximately 2.55 or 0.78. Now 2.55 is bigger than 0.78, so we must have x2 is equal to 2.55, and therefore x1 is equal to, what was it, the other one again? 0.78. So x1 is 0.78 and x2 is 2.55. Now we can see just from our diagram that there is a maximum at x1 equals 0.78, and there is a minimum at x2 equals 2.55. One day we may be in a situation where we don't have access to the diagram, or for a really complicated function or a really complicated situation. So we can actually test these x1 and x2 points using the second derivative test. Now remember, the second derivative test told us that if y prime of x1 equals 0 and y prime prime of x1 is smaller than 0, then x1 must be a maximum. So let's go and check if that's true. Well, y prime of x is equal to 3x squared minus 10x plus 6. Let's write that down up here. Y prime of x is equal to 3x squared minus 10x plus 6. So that means that y prime prime of x is this thing differentiated again. So y prime prime of x is equal to 2 times 3x, so 6x minus 10. 6x minus 10. And we have that y prime of 0.78 is equal to 0. How about y prime prime of 0.78? Y prime prime of 0.78 is equal to 6 times 0.78 minus 10. Well, 6 times 0.78 is actually less than 6. I guess it would be like 4 point something. So 6 times 0.78 minus 10 has to be less than 0. So in other words, we have that y prime of 0.78 equals 0, and y prime prime of 0.78 is less than 0. And therefore, by the second derivative test, 0 y has a local maximum. Y has a local max at x equals 0.78. Y has a local maximum at x equals 0.78, and that's by the second derivative test. Similarly, we can see that, we have that y prime prime of x is equal to 6x minus 10. We know from earlier that y prime of 2.55 was equal to 0, and now we can see that y prime prime of 2.55 is equal to 6 times 2.55. Well, 6 times 2 is 12, so 6 times 2.55 is more than 12. And therefore, 6 times 2.55 minus 10 must be bigger than 0. So we got y prime of 2.55 equals 0, and y prime prime, the second derivative of 2.55, is bigger than 0. Bigger than 0. Therefore, by the second derivative test, y has a local minimum at x equals 2.55. Now notice I'm using the word local minimum, a local minimum at x equals 2.55. And the reason why it's a local minimum is because I can draw a circle around it. I can draw a circle around this point, and inside the circle, it's a minimum. This is x2. Inside the circle, it's a minimum of my function. But if I go over here, there are other values of the function that are smaller than y of x2. So it's not an absolute or global minimum, it's just a local minimum. Similarly, I use the word local maximum here, local maximum, because for the same reason, x1 is only a maximum locally, not necessarily globally, not necessarily a maximum of the whole function, because I can see that even over here there are values of the function that are bigger than x1. Okay, that's it for this lesson. Thanks very much for watching. Don't forget to check out the notes on maximums and minimums and the second derivative test, and do the exercises at the back. Thank you. See you later. Bye.